Okay, great. So sorry for overrunning.
Yeah. Okay, just grab a seat and then we can get started again. Just crack on.
Yeah, just go.
Okay, right, so back to our flowchart. We've seen a situation where we might be able to use a try-lock, but if failure to acquire the shared resource is not okay, then we need to move on to the next point. And this is thinking about what thread is actually mutating the object. And does the real-time thread mutate the object? And if the answer is no here, we can use this thing called a cast loop, or a compare and set loop. So here's a really classic example in audio. We have this shared data, which is our biquad coefficients. Note here, biquad coefficients are 5 floats, so it's relatively large data. We have our real-time audio thread that's using those coefficients, and our non-real-time thread that's updating them, perhaps when the frequency changes, something like that. Now, this is problematic because we've got no synchronization around our biquad coefficients, which means that this write to the coefficients can tear. This is particularly bad with biquad coefficients because there's only a certain set of values of biquad coefficients that are stable. So if we end up writing a couple of floats in a relatively undeterministic order to this and then do some audio processing, we can end up blowing up the state of our filter and causing all kinds of havoc, including damaging speakers and hearing and things. So we really want to avoid this situation. So what's a naive approach here? Well, that would be to just cram the thing in a stood atomic, which will probably compile. And then if we load out our coefficients and then just use our kind of local copy, we've kind of avoided this tearing problem. However, if we use our assert, like we said we should always do when we're using stood atomics, then this is going to fail here. It's going to fail because it's too large to set atomically in hardware. So we're going to be in the situation where it's inserting locks, and then we have priority inversion, so we want to avoid that. So there's a different approach here, which is to use a compare and set exchange loop. So imagine we did something like this. So rather than keeping our actual biquads in the stood atomic, we keep a pointer to our current biquads. So now when we call update frequency parameter, we simply create a new object and assign it to our stood atomic pointer. And then in our real-time audio thread, we load out that pointer and use it. So this is going to work, but the problem here is that there's a huge memory leak. There's nothing cleaning up the old biquad coefficients, and that's not really possible to do in this scenario because there's no way of knowing when the real-time and non-real-time threads have both finished using it. So another approach here is to use some kind of flag to indicate whether the atomic or the biquad coefficients, the pointer to the biquad coefficients, is currently in use by the real-time thread. So here we've got this isInAudio thread flag, which we initialize to false, and then in our real-time thread we set it to true at the start, so it's indicating to anything else that is in use by our real-time thread. Then we can simply use the pointer to process our biquad, and when we're done, we set it to false to say, okay, we're not using it anymore. And then in our non-real-time thread, we create our new biquad coefficients as before, and then we just continuously check this flag to say, is the real-time thread currently using this resource? So we're just spinning on that there. And once this returns false, we can say, okay, the real-time thread isn't using this anymore. So we can swap our pointer to our coefficients with the new one, and then delete the old one safely, knowing that the real-time thread isn't using it. However, we have a problem here in that we haven't kind of synchronized the check of isInAudio thread and the swap of the pointers. So if we happen to read and it says, okay, we're not in the real-time thread, and then at this point here, you can see where the arrow is, the real-time thread comes back in and sets this to true at this point, then we have the classic ABA problem. So now when we swap them, it's actually going to be in use. So this doesn't fix our problem at all. What we need to do, and you'll see this is quite a common repetitive pattern in lock-free programming, is somehow combine the flag that lets us know whether the resource is in use by the real-time thread and the actual data. So if we restructure this slightly, we've kind of moved the processing into this process bytecodes method. We're now saying we're going to store our bytecode coefficients in a unique pointer and make sure we have a default one. And then we're going to have a separate data member, which is the pointer to the atomic that's currently in use. Now we can do something a bit different, which is in our real-time thread, we can first of all get the current value out of the bytecode coefficient, so this is an atomic operation, and we're going to replace it with a null pointer value. So this is essentially our flag now, this null pointer. It's saying when the value is null pointer, the real-time thread is using it. So we get the old value out, we can do our processing, and once we're done with the processing, we can reset that coefficient back into the stood atomic to release it to the non-real-time thread. On the non-real-time thread, we create our new bytecode coefficients as before, and then we now have to somehow try and set this and make it visible to the real-time thread. So we do this, first of all, by checking what we expect to be in the bytecode coefficients atomic member. So we get the value from our storage, because these should be the same at this point. Then we do this compare exchange strong operation. So this is an operation on our bytecode coefficients atomic pointer. So what this takes is, first of all, what we expect it to be here, and then what we want it to be if it is equal to our expected value. So this does an atomic conditional swap, basically. If our real-time thread currently has set this to null pointer, then this is going to return null pointer, and well, it's going to return false here, and it's going to take this expected by reference, so it's going to change it to null pointer. So we know if this returns false that we haven't updated the atomic bytecode coefficients member, so we need to try again. Because this is taken by reference and is going to return the current value, we need to make sure that we update it to our expected again. So we're continuously just trying to set this operation whilst it doesn't currently have a null pointer value. And at some point, hopefully, this is going to succeed, which means we can now move our new bytecode into our storage, and it's going to be safely deleted when the unique pointer gets destroyed. So this works. However, we've got a couple of problems. One is quite verbose, is quite complicated. If you saw this intertwined with lots of other code, it's quite difficult to reason about what's going on. And also, if you make modifications to your bytecode coefficients on the real-time thread, these are never propagated back to the non-real-time thread. So you kind of lose any mutations at this point. It's important to kind of realize. Because that's quite complicated, what we really want to do is combine that into a nice paradigm. And in Fabian's Farbot library, we have this non-real-time mutatable object. It's templated on the type of data that you're storing, and then we simply have this bytecode curves all wrapped up into one. Conceptually, it's the same usage. You do a real-time acquire to return you a reference to the object that you want to use, do your processing, and once you're done with that, you do a real-time release. And internally, that's just doing this null pointer swap. On your non-real-time thread, you do a non-real-time acquire, which is going to return you the value to safely use. Then you can assign a new version to it, because this is a non-const reference, and then do a non-real-time release. Of course, we want to be nice and RAI about this, so we also have this scoped access member that has a template argument whether we're running on the real-time or non-real-time context here. So we can use that. So in summary, we have a scenario here where data is big. We can't use an atomic because it won't act in a lock-free way. The non-real-time thread can mutate the object. It's the non-real-time thread that's created a new object. But the difference to our previous trilock example is that the real-time thread can't fail to access the resource. So it always has a valid object to use here. And the trade-off to that is that the real-time thread cannot mutate the object. Those will be lost. And the non-real-time thread, similar to the trilock, will wait on the real-time thread. Also, you do end up often in a situation when you use this where you kind of create a copy to pass through. There's some variadic constructors in Farbot, isn't there, to kind of minimize this. But just be aware of making additional copies. And the use case is often similar to before: audio samples, wavetables, filter coefficients. So back to our slide, our flowchart. It does the real-time thread mutate the object. If the answer is no, use a cast loop. However, if the answer is yes, then we need to go on to the next question.
Okay, so now the answer is yes, the real-time thread does mutate the object, but we could have the reverse situation. So now that we say the non-real-time thread, your message thread, is not changing the data. So only the real-time thread is changing the data. And there we use a technique called double buffering. So to illustrate this, I have two slots, a double buffer, okay? And one of the slots is always used by the real-time thread, and the other slot is always used by the non-real-time thread. And now, let's say at the beginning, they're pre-initialized with some value A and B, okay? Now, while the real-time thread is creating data, which it wants to share with the non-real-time thread, the data can just come in. It's just using its own copy. And whenever the non-real-time thread wants to read that data, it does a trick. Just before it reads the data, it swaps both of the slots. And now it can safely read the newest data, which is D. And even if reading that data takes a very long time, it's a really long copy, the real-time thread can continue to produce data. So that's sort of the concept of the double buffering. In code, it looks like this. We code the current slot in this variable called index. It denotes the current slot of the real-time thread. Then the real-time thread simply writes into its own slot every time it wants to update the data. And the non-real-time thread, just before reading it, it will swap the index with a bit XOR operation and then read from its own slot. So a very, very simple design pattern. Unfortunately, with simple design patterns, they're wrong. And that's if you run that non-real-time function 2 times in a row. So if you would call update spectrum UI button clicked 2 times in a row. And to illustrate this, let's look at this again. There's some data in both slots. There's some new data coming in. So now the newest data is C. Okay. Now we want to read that data, so we do a swap, right? And then before the real-time thread can come in again, we want to read again. And so we just swap it backwards again. And now we're reading old data, right? The newest data is C, but we're reading B. So to solve this we need another flag to indicate if there's actually new data available for us. And as Dave showed before in his previous slides, you should always have a warning alarm signal when you are trying to put in 2 atomics in your code to solve a single problem. That's usually going to end up in an ABA problem, just as before in his slides. So what we're going to do is we're going to muddle that bit that there's new data. We're going to put it inside the index as its own bit, right? And then the real-time thread can just set that bit whenever it has new data, and the non-real-time thread checks that bit, and if that bit is set, only then will it swap the index, and then it can read. Unfortunately, now we've introduced another bug. This is almost correct. The problem is before, the real-time thread was only loading from the index. And now we're doing a load and a store, and they're even worse, they're not atomic, they're apart, right? So the problem is if the non-real-time thread jumps in between this, then we have a problem. So to avoid that, we introduce yet another bit that's a busy bit. And the busy bit is set while the real-time thread is using the index, right? And the non-real-time thread now does a compare exchange. So it's only going to try to update the index when the busy bit is not set, right? And I mean, just to show here, I mean, here we have, it's not wait-free, right? This could loop, but this is the non-real-time thread, so that's fine. But the real-time thread, although it looks complicated, it's never going to wait. It's just going to go zip right through that. Okay, so that's the whole point of this design pattern, is that the real-time thread doesn't have to do any waiting, and only the non-real-time thread waits. So it's quite complicated, and it's very hard to get right. So again, this is in Farbot. Now this version is called real-time mutatable, because the real-time thread can change this. And it's exactly the same as the non-real-time object as before. You have this real-time acquire, real-time release, et cetera, and you also have this scoped access thing. But it works exactly as the non-real-time mutatable before. So in summary, again, your data is too big to be wrapped in an atomic. Now, in this case, the real-time thread wants to mutate the data, and the non-real-time thread only wants to read the data. The trade-off is that the non-real-time thread has a cast loop. That's fine, usually, because it's a non-real-time thread. But unfortunately, this version, and it's a bit lengthy to go into why, but if you want to capture all the use cases with this farbot thing, you actually need to copy the object on both the non-real-time and real-time thread. So if you have simple, plain old data types, that's fine, because copying is weight-free. It's just a mem copy. But if you would have something more complex, then that might be a problem. So examples are sharing any data that was produced on the real-time thread. Let's say audio spectrums, meter values that you want to share with the non-real-time thread. Okay, so let's go to the next example. This is the hardest example. You have multiple threads, real-time and non-real-time threads that want to mutate the same data. But before we go into that, remember at the very beginning of the talk, we skipped one of the answers, which is what happens if you're not sharing data, but actually passing data from one thread to the other. And really, this distinction is important, right? Sharing data means that at any time, people can read and write from that data. And if you write to that data 2 times, you just overwrite it, right? There's no time synchronization. And passing means really, you really want to take one object and give it to another thread, right? And in that case, we use FIFOs. So the simple, humble FIFO, the first in, first out data structure, is used everywhere in audio code. I'm sure everyone's used it in this room. And it's really good for passing data from one thread to the other because in all of the other cases, we would overwrite the data. So if we have something that's memory allocated and we would use one of the other design patterns I've shown you up to now, you would simply overwrite old data, meaning you would have a memory leak, or if you have some critical error condition you want to send to another thread, if you would just overwrite that error condition all the time, then that would be lost. So that's why FIFO is good, because there's an internal buffer to sort of buffer all of those things that you don't want to lose. Now, in real-time code, we use a particular version of the FIFO. It's called a ring buffer. And the ring buffer has the advantage that it's fixed capacity. It has no allocations, because allocations are not real-time safe. That's what Dave mentioned before. So you have this kind of ring where you have a read pointer and a write pointer, and the read pointer chases the write pointer. I'm sure you've all seen this, this data structure. In code, a very simple single consumer, single producer FIFO, which is weight-free, is something like this. You basically, in the push, you check where your current write position is, where you want to push the data. You calculate the next position of that push, so you check if there's any room in the FIFO. If there is room, you move the object into its position, and then you update the write position, right? Same thing, exactly the same thing on the read side. You read the read position, you check if there's any data to be read. If there is, you move the data out of the FIFO, and then you update your position in the FIFO. So that's very, very simple. But we're going to see a bunch of variations of this FIFO now. And because there's so many variations, this is a quick guide in which FIFO is right for you. And you need to ask yourself 2 questions. First of all, will more than one thread concurrently read or write into the FIFO? Second question is, what should happen if the FIFO is full when writing or empty when reading? And on the producer side, this would look like this, right? Are you on a single thread or a multiple thread? Choose one. If you're on the producer side, if your FIFO is full, we could either return false, for example. That was the previous example. If it's full, it would say, hey, I'm full. I'm going to indicate this to you somehow. Or what you could also do is just overwrite when you're full. You just overwrite the oldest value and continue. And there's similar situations on the consumer side. Either it could be accessed from a single thread or multiple threads, and then it could report if the FIFO is empty by returning false. That was the previous example. Or it could just return a default constructed element every time it's empty. So it always returns something. And if you do the math, these are 16 variations of FIFOs. And just to give you some example why I'm going, like, which FIFO could be right for you, very typical in audio. You're sending some kind of downsampled version of the audio getting to be displayed on the UI thread. So that means you have a single audio thread producing data. You have a single UI thread reading that data. But let's say the UI thread is blocked for some reason, right? You're opening another Firefox in the background, so you get the spinning beach ball of death. Now, when your audio program finally wakes up again, you probably don't want to see all the old audio data that came in 5 seconds ago. So it's probably good if your FIFO overwrites all the old data anyway. You don't care if the FIFO is full, just overwrite it. But if the FIFO is empty, then something's gone probably seriously wrong. Like your audio thread has some hiccup. So maybe you want to report if the FIFO is empty. Another example would be, I don't know, you have multiple real-time threads reading from sensors, right? And you have a single thread kind of checking if there's any bad values coming in. And let's say that's if they're above a certain threshold. You want to sound alarms because then you have radiation contamination in your nuclear reactor or something like this, right? So really, really bad if you would do overwrite when full, because then that critical value might get lost. So you really want to report if it's full. On the other hand, if you're just looking for a threshold, if the FIFO is empty, there's no new data there, then just return 0, because 0 is definitely below the threshold. So that would be fine. So that would be another example of a different type of FIFO. And I'm asking you all of these questions not because it's fun, but because all of these various FIFOs come with different costs. We saw the single producer, single consumer FIFO before, which I said is weight-free on both push and pop. The example with the sensors just now, it's only weight-free on a read, right? Because you have multiple producers writing into that, and they want to report when it's full. I want to just point you out to this most general case. The most general case is multiple consumers, multiple producers, and the FIFO tells you when it's empty and tells you when it's full. And with that FIFO, you could theoretically build any of these other FIFOs. But it's also the most costly FIFO, right? It's not weight-free on push or pop. So Farbot has a FIFO in its library. It has all those 16 variations. I'm not going to show it to you here. It's very, very hard to write a real-time FIFO. Took me weeks to get it working. The most general variant is slower than sort of the reference implementation is Boost FIFO, real-time FIFO. So it's slower than Boost's FIFO, but Boost's FIFO only has the very general solution. And mine has all the other variants, and if you're using any of the other variants, then it's comparable in speed. Now, also a problem with Boost's FIFO, and we'll talk about this later, there's something called the thread sanitizer, which we'll talk about later. But anyway, the Boost's FIFO has a lot of false positives if you try to use it under the thread sanitizer, which will mean that it's very hard to debug your code if you're going to use the Boost FIFO. So I would recommend using my FIFO while debugging if you're using the general case, and then maybe move to Boost FIFO in the end if you really need super top speed. And I didn't come up with this multiple consumer, multiple producer design pattern on my own. Alexander Krzyzanowski wrote a paper on these type of FIFOs, which is really, really interesting to read. Okay, so one of the best things you can do with a FIFO is something called call async. I don't know, Juice users might know call async from the Juice library. What it does is something very useful. You want to do some kind of non-real-time safe thing on a real-time thread, let's say logging, reading from disk, etc. Now, you're not allowed to do it on the real-time thread, but what you can do is defer that execution onto a non-real-time thread. So basically, the Lambda is executed on a non-real-time thread, while the call async itself is executed on a real-time thread and is real-time safe. By the way, the Juice call async is not real-time safe, okay? Just so you know. This is how it works under the hood. You use your call async, you call it on a real-time thread. Let's say you want to do some logging. Under the hood, all it does is it pushes it into a log-free FIFO, a wait-free FIFO. Notice here is that we're moving the Lambda into the FIFO, so the move operation has to be wait-free, has to be real-time safe. Now, on the non-real-time thread, there's this process method that you can call. And when you call this process method, it will just pop all those lambdas from the queue and then execute them. Notice here, though, and this is why Juice's implementation is not real-time safe, is that there's no call to wake up the non-real-time thread. And that's critical, because waking up a thread is a system call and is not wait-free, right? So even just waking up a thread is not wait-free. So the only workaround is to actually have a timer on your non-real-time thread which constantly polls to see if there are any lambdas to process. There's some optimizations you can do here. If you do collect some analytics of when your real-time thread always wakes up, you can construct your timer in a way that it always goes in between your real-time thread. So then your CPU is not doing anything anyway, any hardcore DSP, and then you can sort of slot those timers in every time your real-time thread isn't running, or when you expect your real-time thread not to run. So that's kind of a trick you can do. But yes, so you can't wake the thread here. So summary of the FIFO is, again, your data is too big to be in an atomic, and you need to transfer objects from one thread to the other, like this lambda. Trade-off is that there's a static FIFO size, so you have to think about what happens when the FIFO is full or when the FIFO is empty, and there's a potential overhead of moving into the FIFO or out of the FIFO. But examples are logging, writing to disk, reading from disk, dispatching, all of those things I just mentioned. Okay, so that's FIFOs out of the way, so we're going to jump all the way back to the bottom of our big graph and say now you have multiple real-time, non-real-time threads trying to change data all at once. And just to make it clear, I don't think it's possible. I've talked to many other people. They say maybe it's possible, but it's going to be very, very tricky. And we believe it's best to avoid that situation at all costs. And as a workaround, what you can do, though, is that you nominate one of the threads to be the person in charge of modifying the data. And then all the other threads simply defer any modifications they want to do to that thread, right? So here's some code. An example, you have some kind of audio process which mixes multiple sources, okay? And these sources come in, they can be added and removed, and they can be added and removed on the real-time thread, but also from, let's say, a UI thread. Let's say the user could add these sources and remove these sources. So in this case, we choose the real-time thread to be the one responsible for doing those changes. And any changes that come on a non-real-time thread, we simply defer to the real-time thread. So in practice, this add source could look like this. If you're on the real-time thread, you do the actual change. You change the change. You add the source to the source list. And if you are not on a real-time thread, you do this call async. So you just defer that execution to the real-time thread. Now here's sort of the entry point for the real-time thread. It's mixing all of those sources. First, it will check, well, maybe my own thread, maybe I'm getting some events to add and remove sources. Once it's done that, it's going to process all those lambdas that came in and then add and remove all of the sources. And once it has that, it can simply read all of those sources here. And just to illustrate, remember, we're only talking about changing the data. If you're just reading the data, then you can just access it, for example, with this real-time mutatable again, right? Only if you want to write to the data do you have to defer it to the other thread. Oh, yes, and I could have highlighted all of that code. So as a summary, you use this sort of design pattern. There's nothing in Farbot because I think it's very specific to your use case. It's very hard to abstract to all use cases, but you use it when, again, your data is so big that you can't atomically share it. You're sharing between real-time and non-real-time threads, and all of them are mutating. The trade-off is really that's just not possible in an easy way. You need to nominate one thread to do the changes and then defer all of those changes to that thread. So you're going to have the same trade-offs as the FIFO and the non-real-time mutatable or real-time mutatable object, depending on who you nominate to do those changes, either the real-time or non-real-time thread. Okay, so that was our graph. We hope that this will really help you get out of hell. Just Just as a summary, let's go from top to bottom again. You are sharing or passing data. If you're passing data, use a FIFO. Maybe you're not even interacting with a real-time thread at all. Please just use a lock, right? Maybe your data is always lock-free atomically, then just use std atomics. Maybe it's not so bad to not be able to acquire a resource, use a try-lock. If only the non-real-time thread is mutating the object, use farbot's non-real-time object or use a cast loop. If only the real-time thread is mutating the object, use farbot's real-time mutatable object. And if both are mutating them, then use this combination of real-time object, non-real-time object, and call async or a FIFO. So any questions up until now? We have a short debugging section at the end, but any questions about all of this? Any of the code samples you saw that you would like us to return back to?
Hey, in your call async example, how can you be sure that creating the std function won't allocate?
We are never, I mean, in this code, I never showed you us creating a std function. So
or just creating the lambda.
Okay, yeah, that's a good point, actually. I shouldn't have said lambda. I mean, you would have to create the std function up front somehow, right, when you, so actually just passing in a lambda is probably not a good idea. I mean, in theory, it will work because std function has small function optimization. So it will not allocate anything if you're just using a lambda and not capturing too many variables. But it's a bit hand-wavy. I mean, like for logging, it will work definitely because you're probably not going to capture that much. But you're right. If your lambda is bigger and you're capturing a lot of raw data, then std function internally would allocate. That's a very good point. Yeah, good mentioning that.
I think it internally decays to a pointer, doesn't it, if there's no capture? Which will fit in the space.
Exactly, yeah, if there's no captures. Yeah.
Hi. Considering like a scientific computing scenario that I have lots of intrinsics variables, like the SSC or AVX intrinsics, how profane is to use atomic on those types or to share them? It's something like just don't do, or is there any kind of special?
Good question. I would have to check that. I mean, you could check that with that static assert, see if it's always log-free asserts.
No, I don't believe they will be log-free because when they move between the SSC registers and the common registers, they change and there's all the memory alignment hell.
Right.
But is it something like just don't do it? Or it's something that you can do it if you're careful, or?
I really don't know. It's a very complex question because although in assembly the loads in the stores will be a single instruction, Intel have microcode, right? Like if you're using, for example, if you're using AVX2 on many laptops, the 256-bit wide calls actually reduce into microcode into two 128 stores. So, I mean, definitely on Intel, they're just complex CPUs. It's really hard to reason if it's actually going to be atomic. So I don't know. Yeah,
because what I have been doing so far is using FIFOs, like very simple ones, and just passing, but I'm losing a lot of time on these FIFOs. I would like to speed up a little bit more. So I never actually tried with STD atomic, but maybe something like worth experimenting.
Try it, yeah. Other questions?
Any other questions?
Anybody spotted any bugs? Okay. Then we'll move on. How do you debug a real-time code? Very hard, very, very hard, first off the bat, because it might work 99.999% of the time, and then that one time it doesn't work, especially with real-time code. But I can wholeheartedly recommend, please, everybody use the thread sanitizer. If you're writing any type of real-time code, turn on the thread sanitizer. Unfortunately, the GCC version doesn't catch all the data races, whereas the Clang version will. So use Clang, use thread sanitizer. One catch, though, is that you need to really test the production code. And to highlight that is the problem is, and this is, I said this to the answer of one of the questions, is the C++ standard says that there is no data race if you have some kind of synchronization mechanism. Synchronization mechanisms are atomics, locks, but then this thing that's just called I/O operations, which normally are system calls. And this means that if you add any logging, logging is an I/O operation, right? So you're adding some logging to debug your code. All of a sudden, you have a synchronization event, so all the data races are gone. You remove that bit of logging, all the data races come back. And the same with durations of sleeps. If you have a small duration of sleep, what's going to happen under the hood is it's going to spin, right? If it's just a few nanoseconds, it's not worth actually doing a system call. Now, for your debugging, you're changing that duration. You're making it 10 times bigger. All of a sudden, libc decides to actually do a real sleep. And when you do a real sleep, it's a system call. So it's a synchronization event, meaning all your data races disappear. And so it's crucial to try to debug as close as production as possible. Then somebody said, how do we know if not some of these things internally actually use a system call? And there on Linux, I'm not sure if this is available on macOS, there's something called strace, which shows you all the system calls of all your threads. And then you just have to remember which ID your real-time thread has and just check if the system calls are those that you expect. You can also use some LD preload mechanism. LD preload is where you can replace certain symbols and libraries with your own symbols. So you could replace any pre-thread operations, for example, on Linux, again, on Mac as well. All of the locking operations under the hood, they use something called pthreads. And what you can do is you can create your own little wrapper library which catches any of those calls and logs them, for example. And then you use LD preload, that's an environment variable, to tell the linker to preload your library so that the symbols from your library are used instead of the real pthread symbols. And that's way you can sort of hijack symbols and log when certain things from other libraries are called. You can also do this with allocations and deallocations. But is there any way to do this statically, right? This is all runtime. And always the problem with runtime is, if we wouldn't have this LD preload trick, locking under the hood, if you lock a mutex, it will first try to do this atomically. It will first try to check, is any other thread actually waiting? And if not, it will just grab it without a system call. If another thread is waiting, only then will it do a system call. And often it's very unlikely that another thread is waiting. So you use this strace here, and it's not going to catch any system calls, right? Because it will always do this double locking scheme first. So it's very hard at runtime to actually catch all of the race conditions. So one thing that I also came up with when writing the Farbot library is I would love to say that my FIFO, or exactly this question that just came up here with the Lambda, I would love to say my FIFO is always real-time safe, but it isn't. It depends on what you're using it with. If you're using it with a large Lambda, it's not real-time safe because this move won't be real-time safe. Or allocating in this case, the Lambda will not be real-time safe. So it would be really nice to have a type trait which would say, is this type real-time move assignable? Or is this thing real-time copy assignable? Or is it, when you construct it, is it real-time constructible? And then assert inside my FIFO every time you use it with a type which is not real-time move assignable. And there's a bit of a workaround in Farbot. There is this kind of type trait, and it does the thing for trivial types, for types of certain sizes. It does it for a bunch of STL containers, checks if you can actually move. That's, moving from a vector, for example, is real-time safe. Moving from a std map is real-time safe as long as the elements can be moved real-time safe. So Farbot does a bunch of that, but it really only gets you halfway. For any new type that you write, you would have to specialize this type trait to mark it as safe. And in a perfect world, we would have some kind of C++ mechanism that would recursively check, for example, structs if all of the members were real-time safe. Unfortunately, that's not there in C++. And so we're trying to push the C++ committee to adopt some kind of standard around this, because that would help a lot, I think. So in summary,
Yeah, so the key point here when you're doing real-time programming is to not miss your deadlines. We saw right at the start of the talk, if you miss your deadlines, you essentially have very little hope of meeting them in the future. Be aware of hidden costs. And as Fabian just talked about, and we saw earlier on with legacy objects, you might end up doing allocations and expensive operations that you don't know about. The Lambda one was a good example as well. So really think about your code and try and keep as much out of your real-time pipeline as possible. Follow the flowchart. We spent a long time coming up with those questions to really kind of cover most of the use cases. So it should give you, if you follow the questions, you should get the simplest solution possible for your problem. And also, Fabian went over in quite good detail, but use instrumentation and libraries and things to check your code. It's very difficult to reason about this stuff just in your head. And then if you're working with other developers, it's difficult for them to come and reason about it as well. So use instrumentation so you can rely on your code. Okay. That was our talk. This is a QR code to the Firebot library in case you want to go and check that out. A couple of people have asked in the break, are the slides available? We'll be making this presentation available via, is it GitHub Pages?
Via that link, yeah. Via
that link later on. And you can catch us both on Twitter there. I think that's it.
I think we have time for a couple of questions.
Yep.
If there are any left.
Any questions left up here?
So I guess a question about the static assert to check if if you can use atomic.
Mm-hmm.
Like the example you mentioned about if you compile for ARM and then it doesn't have an FPU or something. So will that static assert always work? Do you know what I mean?
Well, when you're compiling to ARM, then it would assert, right? So you would have, right, when you're
for all ARM chips, that's what I guess I'm wondering. Is there tricky under the hood things where like two floats would work and one wouldn't, or can we just trust it?
I mean, when you compile for ARM, you're going to have to specify, that's unique to ARM, you're going to have to specify if you're compiling to a CPU that has an FPU or not. So if you're in your flags, in your compiler flags saying I'm compiling to a very old ARM version, I mean, I think most ARMs have FPUs now. But if you would specify in your command line argument, no, I'm actually compiling for a very old ARM chip, then it would assert, right? Then it would say, this chip does not support lock-free atomics of floats.
Hi, first of all, thank you very much for the presentation. It was very instructive. Second of all, I wanted to ask if you mentioned language support for checking real-time move assignability, for example. So is there any proposal currently in the works? Thanks.
No.
I mean,
it's a difficult, we've sort of debated how we thought it would work in order to possibly write a paper. The tricky thing with the standards committee is backwards compatibility. And the way we sort of envision it working, I think, is like no except, where you could decorate your function with is real-time safe. And then the compiler could then check all the function calls within that function to check if those are real-time safe and kind of bubble up the stack. The problem with that is it's an opt-out thing. So if you didn't write is real-time safe, then it's going to assert, which means you can't use it essentially with any legacy code. And that kind of behavior just doesn't really fly in the standard. We are chatting with some IDE developers who might be able to do something more on the LLVM Clang level, where you kind of have this intermediate representation and possibly using something like the C++ attributes syntax, you could mark something as real time and then do a static check to go through and check everything that has this. And then maybe in that situation, you could kind of turn it on for just your files because you really want to do this check. It's a bit messy and it's a bit complex though, so there's nothing concrete in motion at the moment, but we've started to kind of circulate the ideas. Is that okay?
Any other questions? I have a question. Can you unit test this behavior between threads?
I laugh because someone, we had some conversations about some very tricky techniques last week.
Right.
Generally, I would say write unit tests and then just run them as often as possible. Use CI. There's so many good CI tools out there these days. And if you run often enough on as many different architectures as you can, you'll just kind of try and minimize that kind of untested boundary. But it's really hard because when you have threads, you're essentially undeterministic about when they run.
I mean, the Farbot library has the unit tests for those design patterns, and it simply like spins up tens of threads, trying to access it and check that, and nothing is going wrong. But really, the problem is these ABA problems. If let's say there is a bug and there's an ABA problem where if thread 18 jumps in exactly at this point and then jumps out like only runs for a single instruction for some reason and then jumps immediately out again. Those are like the really tough ABA problems because it's so unlikely that that's ever going to happen in practice, right? So if you just think of the combinations, there's it's an exponential problem. There's millions and millions of combinations of the way your threads could be scheduled. And is it really going to hit that one, scheduling pattern that breaks your FIFO? Very, very unlikely. So, I mean, we've talked to some people after we gave this talk last week, where they do where they basically hack a debugger to only go a single instruction on the one thread, do a single instruction on the other. Then they restart the program, do a single instruction on this thread, do two instructions on this thread. And they try to reach all of these combinations, but it explodes exponentially if you have more than two threads. So, yeah.
Also, sorry. We mentioned it several times, but use things like tsen. Tsen actually, it's a bit difficult because it actually changes your code. It uses essentially a different version of the library, but it will instrument bits of your code to try and match where you've written data races. But you need to test your production code.
I mean, tsen will only check data races, right?
Yeah.
That's not race conditions, right? Data races are sort of easy to reason about. They're like, are you sharing data between multiple threads without guarding them? But that doesn't mean you haven't written a race condition. Like this ABA problem before, there was no data race there, but there was still a race condition there. And race conditions, the compiler can't reason about because race conditions could be something that you wrote intentionally. The compiler cannot know if that was intended or if it's actually a race condition. That depends on your program. So that's why race conditions are really hard to debug. It's just not much help we can offer.
Hi, I thought the decision graph was really helpful. That's a really great thing. How would you consider that graph if you have multiple real-time threads? Like you don't have a real-time and a non-real-time. You only have the real-time ones.
It's the FIFO, really, isn't it?
Yeah, I think it's the FIFO. Also worth mentioning is that all of the examples like the real-time mutatable and the non-real-time mutatable, if the non-real-time parts of those could be multiple non-real-time because you can just guard them with a regular mutex. So in the library, you can use the real-time mutatable and the non-real-time mutatable with multiple non-real-time threads because they're all just guarded with traditional mutexes. Because that's fine, because you can use mutexes on non-real-time threads. But having multiple real-time threads, you could not use in all of those examples. You only can have one real-time thread. And if you have multiple real-time threads, I think the FIFO is the best answer. And the reason is also, if you go into any example, we were talking about this a lot, like should we have an example there, but if you go into any example where you have like multiple real-time threads, ordering becomes somewhat undefined anyway, right? Because there's no synchronization and there's no I/O going on. So like which thread wrote to the FIFO first? Like you obviously don't care because you didn't write any synchronization events. So there, it becomes very hard to do it with like a single variable and what that could meaningfully be. And we only think like a FIFO really makes sense in that case anyway. But maybe I'm wrong, I don't know. Things get very, very tricky if you think about multiple consumers, multiple producers. I always find that a bit.
Do you have a specific use case? Or?
Just in video games, really.
Okay.
Right, yeah.
And do you need strong determinism of like that ordering?
No.
Okay.
Right, yeah.
Probably FIFO is the simplest solution.
Yeah.
I think we can go for lunch. I think that's. Is there any
Okay.
question? Well, thank you very much.
Okay.
Thanks for coming over.
Yeah.